chemical algorithms. Okay. Test. No. Test. No. Test. Okay, works. Okay, good. So as we all know, like quantum plays a fascinating role in the modern computer science area. It can help accelerating some quantum algorithms. It can enhance the encryptions, and one of those directions is quantum network. So quantum network, it enables the transmission of quantum information using the properties like entanglement and teleportation. And it's crucial for the applications like ultra-secure communication, distributed quantum programming, and more. And it can help make the quantum computer more powerful. So how are we going to build a quantum network? So similar to the classical network, researchers have developed quantum network protocols to help it, and such as the quantum teleportation, the super dense coding, the quantum key distribution, and like the entanglement swap for long distance communication. So here are the circuits that simulate those protocols. And by just taking a look at those circuits, you may say like it's not that intuitive, especially for the people who are not, who don't have too much quantum background to understand what these protocols are doing and what's the difference between those protocols. So that gives us some motivations. We want to build an abstract frameworks that can abstract away all the quantum circuit details. We don't want to show the gates and the qubits, just focusing on the communication itself. And we want it to be classical-like so that we can use the existing tools to analyze the performance of those quantum protocols. And the reason it's called quantum abstract machine because it's inspired from the work, the chemical abstract machine, aka ChemShot. So what is chemical abstract machine? Well, unlike the classical abstract machine, I know like maybe some people heard about abstract machines like the CK machine, but it's unlike that one. It's an abstract machine that's based on the chemical metaphor, and it serves as a high-level abstract framework to model the concurrent system and the process interactions. So it's a very powerful tool, and there are two key ideas that we adopted from Chem. The first is membrane. So membrane is a boundary of a set of process elements, and it can be seen as an individual environment in Chem. And here in our work, we use the same idea, but slightly different. So in our work, each quantum device can be seen as an independent memory. And the second idea we adopt from the Chem is they use the reaction rules to model the communication between different processes. And the idea is like, so like sometimes in chemical reaction, if two atoms or molecules wants to react, each of them needs to provide an electron and form a chemical bond. And so that's two atoms are reacted. And we think this idea is similar to the quantum communication, especially the entanglement-based communication, because like each device needs to provide a qubit to create an entanglement pair so that those two machines are connected and ready for the communication. Okay, so this is why we adopt the chemical abstract machine. And now let's see how we design our work and what operators we add to our system. So our observation is that there are some combinations of gates that frequently occur in different quantum network protocols, and these combinations sometimes share the similar functionalities. So here I'm using the quantum teleportation as an example. The first combination is the Bell creation. It's like creating a quantum channel between two devices, right? And the second combination is like you use some information as the control bits to modify, change the state of the other qubit, of a qubit in the quantum channel. It's like encoding information into the entanglement pair. And the third combination is measurements. It's like converting the quantum information to classical bits so that it can be ready to send through the classical channel. And like after receiver receives the two classical bits, he's gonna use that as control bit as well to change the state of the qubit he had in his hand so that he can recover the information that the sender tries to send. So it's like an encoding again. Okay. So with these combinations, we are able to transform the teleportation circuit to a task block diagram like this. So we can describe the teleportation protocol in 5-step channel creation, encode it, decode, send, receive, and encode it again. And now let's take a look like how we define the teleportation protocol using our abstract machine syntax. So first, we're going to have two membranes. Here, the blue membrane stands for represents the sender's device, and red membranes for the receiver's device. And like you can see, in both membranes, it initially only have neo process, this 0 here. And one thing to notice is that we also put the quantum information as a resource inside the membrane, so that first, we don't want it to floating around. We want it to be a local resource. And second is like once this message is used, it can never be used again to help us ensure the non-cloning theory. Okay, and circle here represents the empty resource. So now the first action we are going to add to the process is the channel creation. You see here, C stands for the quantum channel. And you can see the task block is across two membranes. So we add these actions inside both membrane. And the second is encoding. So we use this left-pointed triangle to represent that. The kappa here is the information, and it's just saying like putting the information kappa to the quantum channel C. And third is decoding. So decoding is a little bit tricky. If you remember the quantum teleportation circuit, right, you may say like the measurement only happens inside the sender's membrane. But why we draw the task block across two parties? And this is because when you perform the measurement, 1 qubit of the entanglement pair, it's gonna affect the states of the other qubits. So we want some way to update that state in the receiver's membrane as well. So first we have this right-pointed triangle to stand for the decoding, and that's just saying the decoded message gonna be held by the variable x, and we put that in the sender's membrane. And then in receiver's membrane we have this C question mark U. Well, if you are familiar with classical process algebra, C question mark U here is saying like receiving some information and hold it by U. But here, the intuitive explanation of this is just like this, the C's state is changed, and we want U to hold this new state. Okay, next is send and receive. That's just classical part. And we add it to both membranes. And then encoding. We use the receive the message Z to encode it to the updated U there. Okay, so now we have the definition of teleportation protocols. And next, I'm gonna show how we evaluate it. So first is channel creation. It's like taking the two channel creation actions from both membranes and create a new resource, channel resource in both membranes, the C star circle here. And second is encoding. It's straightforward. You just put the message mu that you want to send into the channel. So it's a C dot mu there, and now it's seen as a single resource. And third is decoding. But like before we perform the decoding, right, there's an extra step we're gonna perform is the airlock. So airlock, this idea also comes from the chemical abstract machine. What it's trying to represent here is like two membranes are actively connected. So because, like I said before, each membrane is represented an individual environment, and what actions can influence is only inside this environment. But like decoding, right, is gonna affect both membranes, so we want them to be connected first, locked first. So like when performing the decoding action, it can affect the other membranes as well. So we lock them together, and then we can perform the decoding, and that's just converting the quantum message to classical message. And we just put this little hat on top of it to represent this become classical. And then follow the send and receive and encode it again. We finally evaluate these two membranes with nil process. But you can see the message, the resource mu is successfully sent from the sender's membrane to the receiver's membrane. Okay, we're done for that. So we've been trying to use our quantum abstract machine to define several quantum network protocols, such as entanglement swap and some quantum network routing algorithms. And here I'm just gonna give you a little, a brief introduction, like how we define the entanglement swap. I just give you a little bit more taste of what QEM works, how QEM works. And entanglement swap, it's what it's trying to do is we are trying to create a bill pair between Alice and Bob, but due to some limitations, we can't do it directly, probably because they're too far away. So they relies on the third party Xiaodi to help them. And the first step is Alice and Bob, each of them gonna create a quantum channel with Charlie. And then next is Charlie gonna take the quantum channel that he created with Alice as quantum information and encode it to the channel that he created with Bob. And third is decoding, and rest is just similar. So use encoding again to recover the message so that Alice and Bob now can share a built entanglement pair. And this is how we define that protocol using our quantum abstract machine. Again, the blue membrane is for Alice, orange is for Charlie, and red membrane is for Bob. And you can see in the middle membrane there are two channel creation actions, and we encode the channel C to the channel D. Okay. So, and we've been also trying to extend our quantum abstract machine to make it able to analyze more quantum network protocols. I'm not gonna talk about the details here, but what it's trying to do is like, so we've been trying to model the quantum routing network called QCAS and QFAST. Is like a concurrent entanglement-based routing network. And what the general idea is like they're trying to build as many possible paths between two devices as possible. And like we are trying to extend our judgment with some probability labels and mapping and stuff to analyze the performance of this routing algorithm. Okay, so in conclusion, we built quantum abstract machine that's aimed to bridge the gap between the abstract computation model and quantum computing. And we try to provide tools to modeling and analyze the quantum communication protocols. And for the future work, we are trying to find some better ways to extend it to make it able to support the analysis of more complex algorithms, such as like the security protocols, and supports the distributed quantum computing. Okay, one last thing. I would like to thank my late advisor, Professor Rance Cleaveland, for his great guidance and help in shaping this work. And that's all. Thank you very much.
where you showed the, I think it's, I'm not sure if you're calling this decode or encode, but here's a good example here.
Okay.
For instance, so in the earlier slides when you were doing measurement, you had you have a box around two of the measurement operators here.
Yeah.
And Bob, even though this should be symmetrical though, and this is only an action that's being taken on Charlie's qubit. So why is this Charlie, why are you sort of abstracting this as an operation on Charlie and Bob's qubits and not on Alice's?
Okay, I think maybe use this could be a better.
Yeah, so the
Yeah.
works.
Yeah. So that's what we are trying to ensure, like the message recovery is correct, because like I said, like the measurement gonna affect the state of the other qubit, and we want to update the states of that quantum residual qubit in Charlie's in Bob's hand, and that's just the high level idea.
Okay, but does this convey that it's a local operation for Alice and that you're not doing anything on Bob's qubits here?
Yeah, so decoding is just performed on Alice's side, but like our semantics ensure that before you perform the decoding, you must airlock this together so that they can you can perform the decode so that the effect also happens on Bob's side.
So for the later one, is that is it a typo, or is there some reason that you were on the swapping and the entanglement swapping that you were showing this as just on Charlie and Bob as opposed to Charlie, Bob, and Alice?
Oh, I see. So here, because we are saying Alice channel, that's like a resource, information that we are trying to send to Bob, right? So we don't want to say like the state of. So how can I explain it? So because it's information, we don't want to change the state of the information, and we just send it to the Bob. So like in Bob's memory, it's gonna also have a channel C in his memory as a resource. Yeah.
Okay, so but since this is symmetric, we could flip them.
Great talk. Also, just to second the memory of Rance, I've knew Rance since the early 90s. He was a great guy. Do you have theorems about your semantics there? Sort of basic theorems about that it's really good? Some.
No, sorry. Pay too much attention
to
that.
So the semantics is there, and you.
Yeah. We've been trying to define those in COG and try to verify the soundness and completeness.
Okay.
Yeah.
One last quick question.
Might not be quick, so feel free to tell me to take this offline. But I'm curious. I'm not very familiar with the Chang model, the chemical abstraction. What are the capabilities that this abstraction allows you to kind of work with that is not possible with any other, quantum circuit representation or network representation? Well,
so it's like chemical abstract machine to model the process algebra, and which is used to analyze like the concurrent system and not just the communication, like if there's a deadlock there or the fairness or more, because inside the memory you can have more than one process, and like when you evaluate, you're actually gonna choose between the different process and stuff. So, yeah.
Okay, thanks.
Right, let's thank our speaker again.